Now we have studied line integral and the surface integral, as well as the flow integral and the flux integral. Now I will introduce a very useful formula to you that is very powerful in application. The coarea formula. Coarea formula. Suppose G is a open set in R3, and F is a function C1. Continuously differentiable, whose gradient is never 0 for any x in G. Okay, then the pre-emerge of an interval we denote by omega. This is a Jordan domain. Jordan domain. Why this is a Jordan domain? We consider this picture. So this is G, and omega f is a map of a function defined over G to the real axis. This is A, this is B. So the pre-image of this part of the under the map F is a closed set in G. So this is a surface F equal to A to B, and this is another surface F equal to A. So the pre-image of omega is this part. This is omega. Okay, omega is a bounded. G is bounded. Sorry, I forgot to mention G is bounded. Therefore, omega is a subset of G. Therefore, it is also bounded. And of course, it is closed because F is continuous and the closed interval AB is the closed set. Therefore, the pre-image is also a closed set. And also, the boundary of omega is the two surfaces, F equal to A and F equal to B. The boundary of omega is the union of these two surfaces. Because the gradient is not 0, our assumption here. So, using the implicit function theorem, you can prove that locally these two surfaces are smooth surfaces. So that is the boundary of omega is very good. It has Jordan content 0. So omega is a Jordan domain. Okay, so we can consider integration of a function over omega. Now suppose G is such a function. Let G be a function defined over omega. Continuous. Okay, G is continuous. Now from the physical meaning of integration of a multiple integral, suppose we consider this G as a density. Regarding G as density, the mass of omega should be the multiple integral of G. This will denote by M. Okay. So on the one hand, the multiple integral of G over the Jordan domain omega is the total mass of this domain. Okay. Now we consider this from another standing point. So for any t in the interval AB, so this is F equal to T. we take a point in this surface x. Suppose x is a point in the surface f equal to t. Now we take a nearby surface. We take a surface element. D sigma about x. So we have a surface segment about x. Now let's consider a nearby surface. A nearby surface, that is, we increase t slightly. We obtain a nearby surface. Oh, no. A nearby surface. This is f equal t plus a slight increment dt. F equal to t plus dt. And we consider the normal line passing through x. A normal line to f equal to t passing through x. Consider the normal line. The normal line is this. This normal line will intersect f equal to t plus dt at a point. This point we denoted by, maybe I will denote by red. This point we denoted by y. That is, from the point x, we draw a normal line of the surface f equal to t. This normal line will intersect the nearby surface f equal to t plus dt at a point y. So that is to say, fy is t plus dt. So we obtain the following estimate. dt is fy minus fx. This we can use the first order approximation. This approximately this will equal to the gradient of f at the point x, making inner product which is the vector y minus x. Okay, almost equal. The error is very small, which relative to dt, the error is very small. That is, if dt is very small, this will be very accurate. Okay, so but on the other hand, we know that the gradient of f at x is perpendicular to the surface f equal to t. And because we declared y is the intersection of the normal line of the surface f equal to t, which is another surface, therefore y minus x also perpendicular to f equal to t. That is to say, these two vectors in the inner product collinear. They are these two vectors is collinear. Okay, they are in a line. They will not be this position. This is not the case. The case is this case, where x is here and y here, maybe the gradient is here. Okay, or they are in the same direction. Okay, if dt is positive, they should be in the same direction. Okay, so this implies that these two vector has the same direction, in the same line, lies in the same line. Therefore, their inner product equal the absolute value of their inner product equal the multiplication of their norm, right? So we see that dt almost equal to the gradient of this y minus x. This will be the multiplication of their norm. We assume that dt is positive, so the inner product is also positive. That is, the two vector actually has the same direction, so their inner product is the multiplication of their norm. From this, we see that y minus x equal dt y minus x equal dt divided by the gradient of f at x. Now we consider this small cylinder. This is a volume. The volume of this denoted by dv. This part can be the cylinder which base the small surface element d sigma, and which the height is the norm of y minus x. The volume is the norm of y minus x multiplying the area of the base. So dv equal d sigma dt, 1 over the gradient of f. So this multiplying dt is the height, the norm of y minus x, and then we multiplying d sigma, that is the volume of these small pieces of the volume. Okay, but because if d sigma is very small and the dt is very small, so this region dv is also very small. Therefore, we can use the density of at the point x to represent the density in this area, in this volume. Okay, that is because the density is a continuous function. So if the x changes slightly, the density will the change of density is also very tiny. So we can use the density at any point in this region. In particular, we use x to represent the density at this area, every point in this area. That is, we might assume that in this small piece of region, the density is a constant, which is gx, the density at the point x. So the mass element is dm. dm will be the density of x, gx dv. Therefore, this will be gx divided by the gradient of this, then dt d sigma. So this dm is the mass of this region, the settled region. The mass of this settled region is dm. Now we let x go through the surface f equal to t. Then making the surface integral, we will obtain the mass of the mass of the region between these two surfaces. Okay, so the mass between f equal to t and f equal t plus dt is what? Is the surface integral over f equal to t. dm, that is f equal to t gx fx dt d sigma. Okay, so this integral, this surface integral along the surface f equal to t is the mass of the region between these two surfaces. Okay, now this is for a given t and making a small increment dt. Now we know that the whole region, the whole mass of the region, the total mass of the region is just integrating by t once more. So the final result is that the mass of our omega, that is this is our omega, would be integrating this with respect to t. Maybe I will not write so this would be Firstly, we're taking the surface given a t, we're taking surface integral over the surface f equal to t. Of course, this surface integral depends on t. Therefore, the result is a function of t. Now we're integrating which the variable t. We obtain the total mass. But as we mentioned before, the total mass also equal to the multiple integral of g over the omega. Okay, so the total mass should be the same. Therefore, this will equal gx dx. So this formula is the so-called coarea formula. Coarea formula. We state this as a theorem, and of course, our deduction of this result is from physical consideration. Okay, it is not a legal or mathematical proof, but it is very useful. And we will not prove this result here, but we can use it in when we make some computation or reasoning. Okay, so this is the theorem I will state in the next page. Oh. So this is a theorem, coarea formula. Suppose omega is open and f is C1. The gradient is never 0, and g is a continuous function over omega. Sorry, no, not omega. This is g. G. This is true for any x in g, and let omega to be the pre-image of the interval, and g is continuous from omega. Then the result is that this is very similar to the Fubini theorem. The Fubini theorem transform a higher dimensional integral into several lower dimensional integral. Okay, for example, an n-dimensional integral can be transformed into firstly integrating with the n-1 variable, and then integrating with the last variable. Okay, now in our case, this inner integral is n-1 dimensional. Of course, our n is 3 here. Because this is a surface integral, this is a two-dimensional integral. And then we have a one-dimensional integral with respect to t. Therefore, this is, in some sense, Fubini theorem, or you can consider this as a generalization of Fubini theorem. But Fubini theorem, the integral, higher dimensional integral, is divided into several lower dimensional integral. All the integrals are over flat object. Okay, flat object. Well, in this theorem, coarea formula, the inner integral is over curved object. Therefore, this is a remarkable generalization, and this theorem is very useful. Okay.